So, third lecture. And this one is about methodological considerations. So we've established, hopefully, enough theory to understand what diffusion imaging does. An application like tractography. We've learned how to address artifacts, to correct for them with some tools. And these tools are available in Explore DTI. And then I would like to discuss the technique itself. So some of the, considerations, things you need to think of when analyzing data. And then I will show you some strategies to analyze the different analysis strategies. All right. So fiber tractography. Here, what you see is a whole brain fiber tractography result. Looks very kind of, like a coral reef or like some weird, sea creature thingy. But obviously, these are all pathways reconstructed with tractography. And again, color information is about orientation. And now what we can do is we can place arrow-eyes in the brain and segment out pathways of interest. Like in this case, part of the arcuate fasciculus, connecting frontal regions in the brain with temporal regions, or maybe the corpus callosum, connecting both hemispheres, or projection pathways, connecting the spinal cord to some cortical regions. And the nice thing is we can now start to quantify properties of these pathways, right? So we placed arrow-eyes to get access to specific neuroanatomical structures, and then we can look at diffusion properties or maybe geometric properties or volumetric properties of these tracts. And that's great, right? So life of a diffusion MRI scientist must be awesome. Yes, but, and there's a big but, there is a specific issue, and it is related to modeling. And I will show you, I don't know if this is going to work, right? So you might need to open the presentation yourself and watch it. So I'm not sure how it's going to go, but this is what I'm going to show you now is a video of somebody giving a confession on diffusion MRI. So hopefully it works. If not, just watch it from your own presentation that you downloaded. Okay, here we go. And maybe in the chat, do let me know if it works nicely, like if you can hear it and see it properly. Okay, here we go.
Yeah. Yeah. So I think this was back in 2004. Yeah. I was stood outside of the operating theatre, and the neurosurgeon came out to me and told me he was thinking of making a cut in the patient's brain, and he wasn't sure whether to go near the corpus callosum or near the corticospinal pathway. So I used my software and I said to him, look, I can see the corpus callosum, it's all lovely, but I cannot see the corticospinal pathway. So, on balance, I would cut near the corticospinal pathway. Anyway, as a result, the patient died. Yeah. I suppose, looking back now, you could say the tractography was a bit of a letdown, particularly from the patient's point of view. So, what did I do wrong?
All right. I just chatted to you guys. Was this clear, this video and the audio? Just let me know, because then I know for, in future things that I can, take that into account. Yes, it was okay, perfect. Okay, good to know that it worked. All right. Okay, so See? So what was the point of this video? Like, why did I show it to you? Well, so with tractography, we think of pathways being reconstructed, and obviously the neurosurgeons find this very appealing and seems promising, but it is not perfect. Tractography is not perfect. Like I said before, we're looking at data which is not perfect. There's noise. There's artifacts, there's different acquisition schemes, different settings, and then there's the different modeling aspects. And I will come back to the modeling aspects in a moment, but this boils down to the fact that we're looking at indirect connectivity reconstructions. Okay? When I show a tractography result like this, you see the pathways. But I could also show the same tractography results like this. Obviously, this is kind of a weird trumpeting brain-like approach, but what I'm showing you here is I overlay on top of the tracts the uncertainty associated locally along the tract. And the more yellow, the larger the uncertainty, and I actually even provide a width, the thickness of the tube locally being thicker, representing more uncertainty. Okay, so again, what I'm showing you now is the uncertainty associated based on noise. So if you were to repeat the experiment again and again, there are some spots that show a higher uncertainty, right? And this is mostly related to the model itself, not necessarily to the noise, because then you would assume that this uncertainty would be the same across the different locations. But the uncertainty is also associated with the model itself. And think of it. If you have a cigar-shaped diffusion profile, the first orientation, the dominant orientation, is pretty well described. But if you have a more oblate tensor or spherical tensor, then the first eigenvector is less well determined. Think of a sphere. In a sphere, like I said before, there is no well-determined orientation. It's kind of ill-designed, right? Any orientation has the same size, the same amount of diffusion. So the uncertainty goes up. So any small deviation in terms of the signal-to-noise ratio, any little bit of noise will cause dominant orientations to be completely different. So the uncertainty is non-uniform, and that's kind of an issue. So another thing related to tractography is the different settings, and I'll go over a few of them. Okay. One point I want to mention here is that there's many settings, many different algorithms, implementations. I'm going to focus now on three aspects which are often predefined. Okay. These are FA thresholds, like when do you stop tracking? Well, you stop tracking when the FA is below a specific threshold. That's typically done. Think of CSF. It has low FA values. It wouldn't make sense to do tractography and then continue even in the ventricles, right? So you stop tracking when the FA goes down. Angle threshold, you stop tracking when the angle deviates too much with respect to the previous segment of the propagation. Another setting is related to step size, because you take little baby steps through the data. And ideally, these baby steps are as small as possible to minimize this kind of how do you call that? Kind of propagation error. Because what you're basically doing is you solve a differential equation, and the simplest one is Euler integration, and you integrate little steps. But the smaller the steps, the more accurate. Anyways, so these are three parameter settings that you can define in fiber tractography, and they might depend on the application, the tract of interest, etc. By the way, what I'm showing you now is basically the first frame of an animation. So if I start the animation now, these little start, so what I'm showing you now is the little start segment. So at these locations, you see the dominant orientations. And if I start the animation, you see that the pathways grow, right? So this is tractography. This is just another visualization showing how pathways propagate. Okay, now let's focus on the first parameter, the FA threshold. Okay, so we've seen this slide before. If I threshold at 0.2, this is what you get. Everything below zero point 0.2 is left in black and white, but everything above 0.2 is given a kind of reddish hue. If I increase the threshold, then obviously you'll see that less and less remains, right? 0.25, 0.5, and then you end up with this. So if I do tractography with different F8 thresholds, the take-home message is, if I start tracking, and I'll do this now, you see in the left and on the right. On the left, my threshold was the same as before, 0.2. And on the right, my threshold is 0.5, meaning that if you choose a higher threshold, you'll obviously get shorter tracts or less tracts. Okay? So the point I want to make here is that this threshold to stop tracking is something that you can define. Which is the optimal setting? It's not really known, but you could argue that, if you take it too low, you'll get spurious pathways. So then maybe pathways will continue in a region by coincidence due to noise, or maybe some partial volume effect with other structures, causing the pathway to propagate long, too long. And then obviously that's not good either, because then you'll get false positives. And so, and conversely, by contrast, if you have an F8 threshold which is too high, and I guess 0.5 is way too high, because if I do the tractography on the right, well, you can clearly see that some of these pathways, like, part of the corpus callosum or the projection pathways, well, they don't seem to be complete. So if your threshold is too high, you will end up with incomplete pathways or a lot of false negative pathways. Okay? So that's the first take-home message. The F8 threshold, it serves a purpose to balance between allowing false positive pathways and false negative pathways. Okay? Second one is angle deviation. Let's see, I got this question. May I ask you please add Fariba? Let me go to the... Well, I think maybe that was an old question. I don't know. But I think in principle, anybody can now enter the lobby without having permission from me to enter. Is that... Aha, somebody chatted the link. Great. So I suggest Fariba will be sent this link, and then I guess Fariba is a woman, so she will be able to join. Yeah. All right. Awesome. Okay, so we were now discussing the second one, which is angle deviation. Well, if you do tractography, then you take little steps, like shown here, right? You take step, 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 and at some point, in this case, the last step, the angle between two consecutive segments of this pathway, if that is above a predefined threshold, what happens is then the tractography algorithm basically says like, okay, at this last piece, forget about that, because the angle deviation was so large, it's not really plausible as being part of the pathway. So perhaps it's better to stop tracking and kick out the last segment, and then you end up with this pathway. Right? So let's look at an animation. What I'm going to do now is I'm showing you a video where every time frame will represent a tractography result with an increasing angle threshold. And what I'm showing you now, the first frame basically, is my tractography result with a predefined F8 threshold of 0.2 and a step size of 1 millimeter and an angle deviation of 1 degree. So if my consecutive segment deviates more than 1 degree, stop tracking. Well, it's kind of very stringent, very conservative, and so if this angle threshold is too low, again, you'll have a lot of false negatives. You'll be missing a lot of parts of pathways because your tractography is ended too soon. What I'm going to do now is I'm going to start the animation, and you can imagine that if I'm becoming more lenient towards accepting propagation of pathways with a higher threshold, you'll get more tracts and at least longer tracts. Okay, so let's start the animation. There you go. Every time frame is basically showcasing an increased angle threshold. And let me show the animation again, just because it's fun. You can actually see it growing, and it's also quite, it can be considered quite discontinuous. Like, you have a pathway, and then you've got maybe 50% of the pathway, and then at some point you get a big chunk added to it. And if it's a genuine part, which is obviously also related to the length of a pathway, if you know you're looking at corticospinal tracts, then they should go from the cortex to the spinal cord. And then if you see that piece being added to it and becomes more complete, and you've got neuroanatomical knowledge about which pathway is genuine and which are not, then that should be fine. But obviously with a higher angular deviation allowed, we basically have more false positives again. Okay. So it's a similar take-home message. It's a balance between false negatives and false positives. And then step size, like I said, ideally as small as possible, but obviously you can imagine that if you take a step size which is really, really small, from a computational point of view, it would take a long time. So it's kind of linear in time with step size. So the question is like, how small is small enough? Well, if you think of it, we're looking at voxels that have roughly a size of 2 by 2 by 2 millimeters, something like that. Then my suggestion is always to use a step size which is smaller than the voxel size, because if your step size is too large, you might jump over information that is acquired in the data. And so a kind of a rule of thumb, roughly, I mean, this is kind of a guideline, is choose something like half the voxel size, right? So, step size of 1 millimeter for most diffusion data sets, in vivo human data sets should be fine. All right, let's show what happens. So I'm yawning. It's not because I don't think it's not interesting. It's just that I'm a bit tired. So 7 a.m. is pretty early for me, especially because it was quite late last night as well. Preparing the slides and everything. But anyway, enough moaning. Step size. Good. What I'm showing you here is an animation, and I'm going to change the step size from... okay, there's a question. I don't understand how step size is different from voxel size. Okay, a voxel size is literally the dimensions of the voxels of the data that you acquire. So when you acquire data, the data is discrete. Think of a two-dimensional photo with your phone. It has pixels. Well, these pixels, they have dimension if you're acquiring a genuine object, right? So when you take a picture, these pixel dimensions, they don't mean anything. The importance there is the dots per inch, like the density or how many pixels. But in any medical device, when you're acquiring data, also discretely, then these voxels have physical dimensions. This is called a voxel size. So there's literally like, a width, a height, and a depth to a voxel. Ideally, we always acquire voxels isotropically, meaning that these dimensions of a voxel are the same. So we talk of a voxel of 2 by 2 by 2 millimeter, for instance. Okay. When I'm talking about step size, I'm referring to the way pathways are constructed. And actually this one kind of shows it. When I'm doing tractography, this pathway that I reconstruct is basically a concatenation of all these little elements. So as you can see with this little animation, I'm taking a little step, this little line. And this little line has a size, has a length, right? So every little step I take, there's a length associated to it. And so what I'm showing you here in this kind of toy example, on the left, you see this little length of a little segment, of a little step I take each time. It's smaller for S1. So S1 is smaller than S2. Okay, so that's what I mean with step size. And voxel size is related to the data. Step size in tractography is related to taking little steps and reconstructing the pathway. Does that make sense? All right. I hope it does. If not, I can explain it again. or in a different way, hopefully. All right. So, so I was going to show the animation here. So what I'm going to do here is I'm going to start this movie loop, and every frame now is basically using a step size which is a bit bit higher. So I'll start off at 1 millimeter, and we're going all the way to 2 centimeters, to 20 millimeters. Okay, this is what happens. Okay, so you can see that changing the step size, and especially going to bigger step sizes, will drastically change the outcome. Okay. Okay, there's a question about, is the voxel size something that we can modify? Does it even matter? Well, very good question. First of all, does it matter? Yes, it does, because a voxel size gives us the kind of the highest possible detail that we can look at. Think of it, again, I'm making the example with your phone and camera, right? Taking a picture. In the olden days, you took a picture and it looked really coarse, like, like blocky, right? Nowadays, a good camera, digital camera, when you take a picture, the resolution is really high, meaning you can zoom in and you can still see all the detail, right? Well, with data that we acquire, diffusion MRI data that we acquire of the brain, it's important to have good resolution, to look at fine details. And obviously, the higher the detail, the more that you can look at. And so this is something that we can modify at the acquisition level, meaning that, think of it, it's like a setting on your camera, and you say like high resolution, low resolution. Same with an MRI system. You can define what is the resolution that I want in my data. But again, trade is the name of the game. If you want to go for a very high resolution image, right? So very small voxels, that means that your noise, so the signal to noise ratio will go down. So if you have a small voxel, there's less signal in there in a way. There's more noise in there. And this is also something you see in general cameras, right? So very high resolution cameras, they might be very high in resolution, but they will be quite noisy. They will have some noise in there. Another disadvantage of very high resolution data, obviously, is that it will take longer to acquire. So can you imagine you're in a medical facility and a person has some head injury? Well, or you want to do a pre-surgical planning, but the patient is suffering from, epileptic seizures, and it's difficult to lie still in the scanner for a long time. Well, lying in the scanner for a very long time is not possible, right? So there's a limit to the amount of time somebody can lie still in the scanner. And actually lying still becomes even more important, because if you then move a little bit, if your resolution was really high, then the confounding contribution of motion will be relatively larger if you move more. Like if your resolution is higher, then the same amount of motion will cause more problems in your acquisition than choosing a lower resolution. Does that make sense? Okay, so yes, you can choose, but there's a trade-off practically and also methodologically, meaning you can't just say like, I want to have a data set with a resolution of 1 micrometer, because there won't be any enough signal in your voxels. It will be mostly noise. Okay. Okay. No, never apologize. You guys are students, and so it's always good to continue questioning things. So sorry to keep going back to this, but if the voxel size is the smallest amount of data that we can acquire, then how can the step size be smaller than the voxel size? Aha, good question. Welcome to the world of interpolation. It's a fancy word of basically saying if we have signals at voxels, right? And indeed, you're right. We've got discrete voxels, and let's call them 1 millimeter apart, right? These voxels, they have a physical dimension. Think of it as little cubes. And in this little cube, there's a signal. So what is actually located in between the voxels then? Well, these voxels, they represent a data set. They represent a world object. I mean, if my brain is in the scanner, my brain has an infinite dense sampling of locations, right? I mean, every part in my brain is a location. But if we acquire data, we only acquire at discrete locations, right? Because we can't acquire at an infinite resolution, right? We do what we call sampling. We sample at locations signals. And so at all the other locations, what is the signal there? Well, we don't know, but we can make a very good guess, a well-educated guess by looking at the neighbors. So let's assume you've got 4 voxels and you're right in the middle. Well, then you can say, well, my signal will be kind of a weighted average. If that location is closer to one voxel, then I'll give it more weight to that voxel. And so you can think of it as at every location, like in a continuous world, at every location, the signal there will be a kind of weighted average of the neighbors in that area. What I'm now describing is known as interpolation. If you Google interpolation, then you should be, a new world will open, basically. So when you're doing tractography, and this is the cool thing, with tractography, we're continuously looking through the data. Where is my dominant orientation of my diffusion profile? But if you're at a location where there is no voxel, and this is, technically speaking, everywhere, because you're continuously taking a little step. So you take a little step and you enter a region. Hey, but this is not in a voxel. Like, I don't ever see it. It's in an area which is surrounded by voxels where you get a kind of weighted average by the neighbors. That information will be used at that location. So at that exact continuous location, you'll get that information. And obviously, if you then follow the dominant orientation, you take a little step. Well, and now this step size kicks in, which basically says, you take a little step, but that step size, you shouldn't do it bigger than a voxel size, because if you jump over a voxel, this is valuable information that was acquired in data. If you take it smaller, then you will most definitely take information of that voxel that is near to it. So you basically follow the information. Does that make any sense? Okay, so voxels we acquire. Step size is related to tractography, and tractography is continuous. You go through the data in a continuous way, but if you're not at a specific location of a voxel, you just look at the information around that location, and these are the, let's say, 4 or 8 neighbor voxels. Depending on the type of interpolation, you may have heard of nearest neighbor interpolation, or linear interpolation, or bicubic spline interpolation. These are all types of interpolation strategies. Yeah, it is cool. I know. I mean, that's why I do this for a living. You script and you program these kind of algorithms. And it is pretty cool. Yeah, so good. Happy to see that you understand it. Let me just close the curtain here. Let's see. All right. Okay, I'm going to continue. Okay, so that's step size. Okay, and similar, take-home messages. Some things to be aware of. Like I said, if you take the step size too small, obviously your data storage, computation time, they all increase linearly with the actual value. We discussed angle deviation. Well, step size and angle deviation are kind of coupled, right? So if you take a specific angle threshold, it will seem as if it's a larger angle threshold if you take smaller step sizes, right? So in a way, you need to look at a property like curvature, but in practice, you kind of get the hang of what is a plausible turn in the brain pretty quickly. So if you take 1 millimeter steps, then we argue, well, if you take a little turn of, let's say, more than 45 degrees or even 60 degrees, you could easily argue, well, this is a pathway configuration which is not plausible anymore, so stop tracking. Okay, and then, a lot of people have done a lot of research on validation, evaluation, and this work by Meyer, Hein, Klaus, it was actually shown that we suffer mostly from false positive reconstructions, and to a lesser extent, false negative reconstructions. Okay? So prior knowledge about anatomy is very useful when doing tractography. Knowing that, the uncinate fasciculus, this hook-shaped pathway, that it connects temporal pole to orbitofrontal cortex. This is something that we know from these dissections, right? So we can learn from that and then see whether it kind of looks the same. But it's kind of very hand-wavy. The actual validation is still ongoing research. To date, this is the only in vivo technique that can virtually reconstruct pathways. Okay. All right. Another disadvantage is the error accumulation. I mentioned, we got noise. Well, also related to model imperfections, we know that if we reconstruct a pathway, that, because of all these little errors, data imperfections, noise, that at each step, because of uncertainty, this little error, it will accumulate. So if you have a long pathway, the odds are very likely that, down the road, you'll end up somewhere which is not perfectly correct. And what I'm going to show you now is an example of this. Okay, so I've drawn one arrow Y somewhere in the middle here, this red arrow Y, and it basically shows you, what are the pathways going through this arrow Y. So I did whole brain tractography, and then I asked the software, like, in this red arrow Y, what are the pathways going through it? And then I get this result. And this is what I kind of expect with the cingulum bundle, right? It's part of the limbic system. You've got this subgenu part over here, and then it connects to the parahippocampal system here, going to this region. But if I were to add another arrow Y, which has the following meaning, what are the pathways that go through this red arrow Y, but also at the same time go through this white arrow Y, then this is my result. So as you can see, it seems like, there's a part missing here. Okay. Conversely, if I take an arrow Y around the other part, it seems that the frontal part is now missing. And so this is the curse of long pathways, where the ends might not necessarily connect directly to each other because of, data just not ending there. So that can happen, right? And I'm showing you an example here. So in addition to this error propagation, there's also the model assumptions. And I mentioned to you before, with diffusion tensor imaging, we are assuming that our diffusion profile is Gaussian, that the molecules spread like an isoprobability surface in a Gaussian fashion. And, well, if you look at the brain, well, we see these kind of spaghetti-like structures. We see, we think of it like these cables. Perhaps not that colorful, but this is how a physicist thinks, right? We think of connections. We see like a cable network connecting different brain regions. And we've been using this diffusion tensor imaging model to describe this diffusion profile. But there's a limitation to it, and the limitation is that it can only capture Gaussian diffusion. What about non-Gaussian diffusion? Well, to cut a long story short, when you're looking at the Jekyll-Tanner equation, your diffusion equation, basically with diffusion tensor imaging, we're looking at a first-order approximation. If you were to do the Taylor expansion, all the math and everything, expand it to the second term, you will end up with a diffusion kurtosis imaging model, which is basically the same as diffusion tensor imaging, but it has some additional terms. And don't be scared, but I'm going to show you the formulas. So in the top, you see the diffusion tensor imaging formula. And at the bottom, you see the kind of the same exponent, but in addition to this first order term in D, you also have this other term, which is basically a term in like squared in D and in B. Okay? And this is the kurtosis imaging part. So what does that do? Well, in addition to the Gaussian part as described by the tensor model, we would also now be able to describe the non-Gaussian part of the diffusion process. So a kurtosis is basically a word which is used in statistics to describe the kind of the excess of non-Gaussianity. So if you have a non-zero kurtosis, it basically means that your distribution is non-Gaussian. If your kurtosis is zero, then it basically collapses back to the Gaussian system. Okay? So, okay, what does it mean in practice? Okay. So again, we are acquiring diffusion MRI data as before, but in addition to the B value of 1000, we acquire more diffusion data with another B value, because we're trying to capture this nonlinear decay of the diffusion signal to be able to describe this non-Gaussian behavior. And so diffusion kurtosis imaging is basically diffusion tensor imaging, and you acquire more data. And this will then result in a model which has the diffusion tensor imaging parameters as before, but it also creates, or with this new model, you also have kurtosis metrics. And in analogy with fractional anisotropy and mean axial and radial diffusivity, you now also have something which is called kurtosis anisotropy, but also the mean axial and radial kurtosis. And so they reflect, so let's focus on mean kurtosis, for instance. Well, that metric basically says, what is my average amount of non-Gaussianity? This is how you have to interpret it, because the kurtosis says something about deviation from Gaussianity. And the higher the value, the more it deviates from Gaussianity. And so looking at these maps, there's clear structure in there. It's not just random. Looking at kurtosis anisotropy, which basically means if you have a kurtosis in a voxel, how does it depend on the orientation of your diffusion, right? So, these metrics, these new kids on the block, if you want, it's a bit more complicated now. Okay, so you get more metrics, and they reflect properties of non-Gaussianity. That's how you should interpret it. So it stays kind of fuzzy, right? With fractional anisotropy, you basically say, well, that's a measure which reflects, your degree of different preferential diffusion orientations, right? How does my diffusion differ depending on the orientation? Well, same with kurtosis anisotropy. To what extent does my anisotropy change? To what extent does my kurtosis change as a function of orientation? So you got kurtosis anisotropy. And then there are some more models that use properties of this kurtosis framework to then estimate like intra-axonal diffusivity, extra-axonal diffusivity, tortuosity, all these other parameters that are based on, kurtosis framework. And this is one of many models. And there are many models, and each of them, they all have their assumptions. If we look at the brain, again, we always think of these kind of, parallel fiber bundles, right? At least at the length scale of a voxel. But in practice, there's many complex configurations, right? If you look at these, configurations that I sketch here, right? You've got pathways that genuinely cross, but also kiss or splay or bend. There's many different configurations that are clearly not straight at the length scale of a voxel, right? So, and with the latter, I mean, literally, if you have a cube, a voxel, if they're all running in parallel, then sure, there's one orientation. And if you use the diffusion tensor model or the diffusion kurtosis imaging model, it's clear that there's one dominant orientation. But in this case, if I ask you, what is the orientation left top? Well, you see two crossings. You would say, there's two orientations. Clear. Two populations, they're crossing two orientations. Same holds for the one on the right top. But what about the left bottom? This type of configuration, what's the orientation? It should be clear now that we would be looking at an entire distribution of different orientations. And on average, that orientation is going, up, down maybe. But that's only a a very small fraction of pathways that is actually oriented like that. So you can already see the complications, right? If the information provided by the model does not, capture the complexity of the underlying tissue, then we need to resort to other models. One comment that we often received or that was debated was related to resolution. Because if you look at the right top example, you could see I see two crossing fibers. But if my voxels had a higher resolution, I might have been able to disambiguate both populations, like a little voxel in one population and the other voxel in the other population. And I kind of agree that could solve it. But in practice, our brain is also configured like left top. And if you look at the left top configuration, where they're genuinely crossing, then we would be looking at a very difficult multi-scale problem. Because if you were to take smaller voxels, even in those smaller voxels, you would still see crossing fibers. Okay? And I'm going to showcase this with an example. Here you go. Okay, this is not a butterfly. Okay, it looks very butterfly-y. Nice colors. This is not a diffusion MRI image. This is a polarized light imaging microscopy section near the medulla oblongata, right? So near the brainstem area. And what you can observe here is a very high resolution, because if I overlay the voxels of our diffusion dataset, this is typically our resolution with diffusion MRI, the white squares. But the underlying resolution of polarized light imaging microscopy is really high. Okay. First of all, just to get that out of the discussion, polarized light imaging, in short PLI, is an ex vivo technique. Okay, so there's still a reason why we use diffusion MRI, because if this was an in vivo technique with benefits of having this high resolution, well, there's no need for diffusion MRI anymore then. I mean, from that point of view. Anyway, so you could argue, well, use PLI as a validation. And indeed, it's another technique that has, let's call it converging evidence then, if the results are the same. But it's not a golden standard on its own, because this technique is not perfect either, right? It has to section the data. These sections, these slabs, they don't have an isotropic resolution. They have an anisotropic resolution, which is not beneficial with respect to biases and crossing fibers. It actually cannot disentangle crossing fibers within a voxel. So it has the same issues as DTI, but it has a very high resolution. So that's cool. So if we look at these results, looks great. Another point I want to make is look at the heterogeneity of pathways within a voxel. So if you were to increase the resolution with diffusion MRI, even to the micrometer level, you would still have the potential of pathways crossing at that location. Okay? I mean, even axons themselves can branch. And then we would be looking at the micrometer, literally 1 micrometer or even less resolution. So having said that, we would need to resort not just to higher resolution, we also have to think of other models. And these models will become important to disentangle these crossing fiber regions. Okay. What I'm going to do now is take one step back and let's look back at DTI. Okay. And let's look at the FA map. And look at this region. So this on the left is an FA map. Right? This is a subject in vivo. And on the right, you see an ex vivo, just a dissection of a brain, mid-coronally. And if you look at those regions indicated in the little blue squares, it should be all white matter, right? You can see this on the right, it's all white matter. But on the left, the FA map has a very low value in the middle, right? Low FA value. And how is this possible? Because I mentioned in white matter, you've got structure, highly organized fiber tissue. There, the diffusion should be very anisotropic, so the FA should be high. Why do we still see a low FA region in there. I mean, is that like a lesion, some pathology? I mean, I hope not, because that's my brain, right, on the left. So no, it's not a lesion. As far as I know, I'm still healthy. What's going on there? And it was actually mentioned in the comments in one of my previous lectures about that. What if multiple fiber populations join together? Well, indeed, we've mentioned that if you have three orthogonal fiber populations, from an ellipsoid point of view, well, you'll get a sphere, right? Because you'll have the same amount of diffusion going up, down, left, right, front to back. So the FA will be low. So, hey, what we're actually looking at is the intersection, literally the intersection of different pathways. And we can already see this, right? If I go to the same image again, if we focus on these pathways, this is kind of a schematic here, right? So if we focus in this white rectangle, in green, indicated by the green circle, well, there's pathways going front to back, association pathways. In blue, there's pathways going up, down, the projection pathways. And in red, well, you could see on the left parts of the corpus callosum, commissural pathways going left, right. But they all seem to mix up in the center, right? And it's exactly in that region where we have this kind of anisotropy, which is very low. We get very low values because the diffusion front back, up, down, and left, right might be of the same magnitude. So how can we tackle this, right? What can we do about these crossing fibers? Well, a lot, right? A lot of people have been working on this for, almost 2 decades. I will focus now on a technique which is very popular, and it's reflecting a spherical deconvolution approach. Very fancy words for basically saying, let's model our diffusion data, not with an ellipsoid. Let's not just look at Gaussian diffusion like this matrix, this 3x3 diffusion tensor. No, let's use a set of basis functions which has more freedom to capture the shape and size of the diffusion profile. And remember, diffusion profile is it's a centrosymmetrical phenomenon, right? You've got the starting point, and then think of an isoprobability surface growing. But the shape and size, well, it is symmetric because diffusion going left is the same as the diffusion going right? There's no difference. It's centrosymmetric, antipodal symmetry. I think that you also can call it like that. So the cool thing is now, and this was proposed many years ago, and Donald Tournier is one of the pioneers in this field. He basically said okay, let's look at the diffusion signal and let's model it with spherical harmonics, and then we'll do a cool trick. And the trick was, and this is what he and others have said, it's our diffusion signal that we measure, that's basically, you can consider it as a convolution of a response function with orientations of fiber structure. Okay, what is the response function? What is that? Well, think of it as a diffusion MRI profile of a single fiber population. But if you have multiple orientations, you can then say if I convolve this response function, this signal of a single fiber population with all the potential orientations, then I get my fiber orientation distribution function. Well, this is wrong what I just said. Sorry, I was wrong. You've got your response function, you've got your orientations. If you convolve it, you'll get your final diffusion signal, right? So the diffusion signal that you measure is a convolution of your response function with your fiber orientations. But what we're interested in is actually the fiber orientations, which we don't know. But what we do know is the diffusion data that we acquire. So we have a diffusion profile. And now the cool thing is, if we assume that we know how a single fiber orientation, how it would look like, like what is the diffusion signal of that, then deconvolve it from our diffusion signal that we measured to begin with, and then we end up with a fiber orientation distribution function. I know this is a lot to absorb, but feel free to look into the details in these papers that I cite. Okay, but I'll go into detail in the next slides. Okay. So first step, I mentioned our diffusion profile. That's what we measured. Let's rewrite this as a linear combination of our spherical harmonic basis functions. This is a similar approach if you say, for instance, let's describe a signal as a linear combination of sines and cosines. Does it ring any bells? Well, that's Fourier analysis. In this case, you're doing something similar, but we call it a spherical harmonic basis set functions used to describe this function. And you can estimate these coefficients quite readily because, you can do this in a linear combination, and then you just use, linear estimators, and you end up with what the spherical harmonic coefficients are, components, and as with many basis sets, you need to define a kind of threshold, like how many, like in Fourier analysis, you would say, okay, sines, cosines, up to a specific frequency, and then you cut it off. And the same holds with these spherical harmonics. This is kind of what I wanted to show you with the M1, M2, M3, and all the different L's, like L is 0, 2, 4. These are what we call the degree and the order of the spherical harmonics. Okay, so apologies, I should have mentioned this earlier. So these spherical harmonics, it's a basis set of functions. They have parameters, and you can define, if you want, the kind of resolution with which you want to capture the signal, the diffusion signal. Okay. Okay, so these are parameter settings. And remember the overfitting, right? So there was a question about overfitting. Well, if you were to choose a degree or which is too large, like instead of going to 4, 6, or 8, maybe 12, you might actually be starting to fit noise, right? So you don't want that either. You'll get artificial peaks and everything. We'll come back to that later. But anyway, first step, estimate the coefficients from for the diffusion profile, and then you do the deconvolution. So again, this is what we measured on the left. This is the response function or the diffusion signal profile of a single fiber population, which you deconvolve from what we've measured to end up with a fiber orientation distribution function. It looks like this multi-lobular thing like this. Okay. So take-home message here is that with this spherical deconvolution approach, and the one I'm presenting here is called constrained spherical deconvolution, or in short, CSD, you basically end up with a fiber orientation distribution function. It's a mouthful, also in short, FOD. So you end up with an FOD, which, as you can see here, consists of 3 peaks, right? You see these 3 peaks. By contrast, on the left, with our vanilla DTI, you can appreciate that we've got this ellipsoid, which basically only shows one dominant orientation, namely the main axis of this ellipsoid, right? So this kind of almost cigar-shaped ellipsoids is basically reflecting, you've got one dominant peak in this voxel. By contrast, on the right, with CSD, it's clear that you have 3 peaks, right? You've got 3 different orientations. Okay, and this is per voxel. So if we now focus on a region of interest, in this case, this kind of mid-coronal section, these are the diffusion ellipsoids that we're used to, quite simplistic in a way. You can see the main orientation. But with the same data set, with the same region of interest, if I were have used the constrained spherical deconvolution model, then this would be the result. Can you hold on one sec? I got my son calling me, so 1 second. Ja, Mats? Ja, zeg maar. Oké. Zoek het uit. Ik zit letterlijk in een meeting. Het is een nu mail live. wordt dat 50 plus mensen nu horen. Dus het is niet zo fijn. Dus ja, heel leuk. Ik ga nu afleggen. En zoek het maar uit. Goed? Je vindt wel wat. Yo, tada. You know what they say, right? Family comes first, even if you're giving a talk to people. All right, so obviously apologies for that. That's not what you signed up for, but that's how life works. All right, so continuing. So we've seen, in the previous slide, these ellipsoids. You can imagine if you reduce that to the dominant orientation, you've got one peak per voxel, one orientation. But now, if you look at it, you've got this kind of multilobular structure showcasing a lot of extra detail, right? For instance, you can see in the previous one with DTI, you see these blue ones, right? The blue ones, they're reflecting pathways going up, down, part of the corticospinal tract, right? These projection pathways. If you go and look at CSD, you see the same peaks following that orientation, but within this region of the centrum semiovale, you can also see peaks oriented left-right, meaning red. They're going more lateral. And these are parts of the corpus callosum, for instance, that genuinely cross the corticospinal pathway. And it's the same with, in this case, with DTI. The green ones, association pathways, the dominant peak will probably be going front-back, hence the green color. But if you focus on this one, again, same data, but a different model, you also see these green peaks, pathways going front to back. But at the same time, you also see peaks going up, down a bit, and peaks going left, right. So, first time I saw this, I was like, right? This is amazing, the amount of additional information that you get per voxel, right? So, one question that sprung to our mind was like, okay, these crossing fibers, wow, they seem to be, quite abundant. How many are there? And so we just did an analysis on a very high quality data set with many directions. And let me color encode it according to number of peaks. So then it kind of strikingly shows this information. So you've got one dominant peak. Well, in this case, in red, think of the corpus callosum. Again, this is data driven. So purely based on the data and the resolution that we have in our data, this is what we got. The vast majority had at least 2 crossings or more. Right? In green, you see regions, voxels with 2 crossing pathways, and in blue, with 3 or more. Okay? So yeah, that was quite exciting to see that the vast majority of voxels at the resolution that we're imaging contain pathways that literally have different angular information, right? And so we thought that was cool. Obviously, if you're doing tractography, same issue in a way, right? So this is the same data set, and we're looking at a mid-coronal section. I placed a few seed points here in the middle, and this is the result that we got with DTI-based tractography, meaning we would only look at the ellipsoid and at the dominant orientation and follow it wherever we can. But if we use CSD-based tractography, then this is what we got, right? So one thing that already immediately, is striking is that, well, it looks like you've got something similar like DTI, like this U shape, if you look at it coronally. But in addition, we also see these lateral projections, which we couldn't see before, because with DTI-based tracking, you would not be able to cross the corticospinal pathways going up. So it would kind of stop there. But in reality, they would actually cross those, other pathways going to the lateral regions. And the second thing I really like about this is this image. If you know about the hand knob in the motor cortex, this omega shape, you can actually see the omega here as well. And it goes to the homologous other side. So the other side is like the mirroring of that cortex. So what I'm showing you here is probably the connections responsible for coordinating, opening and closing buttons of a shirt, because they need to work together. They need to, probably feel each other, or, to get an idea of how far they are apart or something like that. So, yeah. So what we Are you still there? Oh, okay. Anyway, little glitch in the system here. But the good news is, or the point I want to make here is that with this other technique, you basically get a more complete picture of pathways. So the idea is, with this spherical deconvolution model, you would be more accurate in reconstructing pathways. That's the idea. Obviously, you can play devil's advocate, and you can think of a voxel where there's one population making a bend. Well, from a diffusion point of view, you cannot really disambiguate a bend in a voxel from a crossing in a voxel. The diffusion profile will end up with the same result. So, this is something that is kind of ongoing in terms of trying to fix this. This is an important topic of research. But obviously, as you can imagine, depending on which algorithm that you use, you'll get different tracks, and this is of most importance for neurosurgical, preoperative planning, right? If your tract looks completely different if you use another algorithm, well, you should be careful where to cut and where not to cut. All right. Now we're entering the final stage of this lecture. It's the different approaches for data analysis, and this is something that we'll also touch upon in the hands-on session. One of the most, let's say, fashionable nowadays is looking at the brain as an integrated network of connections, and this is then called connectomics. Okay, so the kind of funny quote that goes along is like, segregation. So 2018. Now we're looking at integration, how different regions of the brain work together, and how network topology and properties of this network drive, cognition or have an effect on specific pathology, etc. So this is, kind of the fashion nowadays to look into this connectomics approach. So how does it work? I'll give you a kind of theoretical overview on how it works. So connectomics is, you can think of it as a graph theory analysis. And those of you who are familiar with graphs consist of nodes and edges. So these are like an abstract representation of a graph. There's graphs everywhere, right? Like Facebook, you've got connections, you've got nodes. Nodes are the people here. And then connections are basically literally like, what property do you have in common with the other person? Is it family? Is it a friend? Maybe it's a random stranger you never met, but you don't want to offend them, so you just connect, whatever. So there's many different degrees and properties of these edges as well. Another one which is quite popular is a flight network. You've got airports, and you've got the flights between the different airports. And here you see, for instance, Amsterdam. It has KLM, very well known, flies everywhere. Well, not today anymore, but anyway, that's a separate story. So you can now see by looking at the connections that different nodes have different properties. Like Amsterdam seems to be a hub, like a very important node, because it's connected to everything else. But there are many different properties within such a network. So that's also very interesting to look into. So how does it work for the brain? I kind of bumped into this kind of schematic, which I thought was interesting. So here's kind of a railway system mimicking brain architecture. And it's kind of similar in a way, right? You've got regions and connecting to each other, etc. So how does it work for the brain? Well, you've got nodes. These are the brain regions. Think of it as the cortical regions. Then we have edges. These are the connections between the different brain regions. And these connections, well, they're derived with tractography, for instance. And so if you combine those both, you can then start connecting every region to every other region. So if you've got 100 regions, you've got potentially 100 times 100 divided by 2, roughly, number of connections, right? Reason why I said divide by 2 is because if A is connected to B, then B is also connected to A, right? It's kind of, associative or commutative, right? You can interchange them, the order. And that's because tractography is not, giving any information about efferent pathways or not, right? It's not saying anything about in what directions are pathways communicating between the different regions. All right. And then step 3, once you have the nodes, once you have the connections, you can now think of entering a value in this matrix, right? This graph can be represented with a matrix. Every row and every column is a brain region. And then you can think of the simplest of simplest measures, like a binary connectivity matrix, meaning you place a 0 if there's not a connection between those two regions, and you place a 1 in the matrix if you find a connection. And what does it mean if you find a connection? You could argue, well, if I can find one of these fiber pathways as reconstructed with tractography between those two regions, connecting the regions. But you could also enter other measures in there. Maybe number of pathways that you find between two connections. Or maybe some diffusivity property along the pathway that connects the two different regions. And then once you have this matrix, this connectivity matrix, you can compute, many of these graph properties. Like if you have a network, you can compute how efficient it is, or nodal degree, or clustering coefficient, or hubbiness, or the rich club, which nodes combined are the important ones, things like that. And it's now very fashionable to look into these graph theoretical metrics that kind of condense or summarize the inner workings of a network to a single number. And maybe these could be useful to identify brain regions that have been compromised in pathology. So maybe it's not just one region being affected that is the problem. Maybe it's a combination of specific regions which were interconnected that is important to know, right? So it opens up a new way of thinking about how, brain damage is represented from a network point of view. So that's also very interesting. And this new avenue is, like I said, it's fashionable because we couldn't do this in the olden days. But, last 5 to 10 years, admittedly, we're already at 15 years, but from a kind of scientific point of view, that's still relatively young, I would say. But we start, doing this type of research. And there's many issues, and I'll come back to that in a moment. I'll come back to that now. The challenges. Well, remember I said we have different diffusion models. Well, you've got DTI, CSD, many, many different models. Well, like I said, all of them are useful. They're all wrong, but some of them are useful. That's what I want to say. If you were to choose spherical deconvolution-based tractography, remember that you have this kind of connections being more lateral. This is something you can obtain with CSD, but not with DTI. So these type of connections would be gone from your network. So obviously, depending on which tool you use, which model you choose, to describe the diffusion profile, you'll get a different connectivity matrix. If you look at this one, it gets even more complicated because you will get connections with DTI, because if you look at this in more detail, this is with CSD, this is with DTI. So it's like it's incomplete, right? So there are connections, but not the same one per se. Another issue, when we ask how do we define the connections, the edges, I said like you could use, the binary matrix, right? Is there a connection, or number of pathways, or FA of a bundle connecting these? So there's different definitions, and to some extent, the analogy could be given with, the choice of measure depends on which airline you think is important, right? If I'm showing you this map, well, then obviously Amsterdam is very important. It's a hub. But if I were to use a Norwegian airliner, well, maybe Trondheim or Bergen would be very important, or Oslo would be very important on this map, right? So it's also a matter of how do you define the connectivity matrix to begin with. Another challenge is related to the parcellation of the brain regions, right? We assume that in this network we've got nodes, but how do we define the nodes? A template then the question is like, which template? And is this template relevant for your population? Should we use an atlas or some individual segmentations that we do by hand maybe, right? So there's many options there to define the nodes of this graph. And there's many more, which tractography implementation, the settings. What about the statistics? Because if you're doing a multiple comparison, or multiple subjects analysis, and you would be looking like which node is important. Well, obviously we've got many nodes, and by chance there will be one who will be significantly different. But because we're looking at so many comparisons, you need to correct for that. And ideally you do something like a Bonferroni correction. But in practice, we always know that there's some kind of correlation between adjacent nodes and things like that. So, the statistical approaches have not yet, let's say, crystallized yet, in my opinion. Okay? So some people argue, well, if you look at this network representation of the brain, it's quite abstract, and some of them, they feel the artistic value is higher than the scientific one. And, if you look at an image like this, how can you disagree, right? So, yeah, that's definitely an issue. Another approach for data analysis, and this is what I would call a vanilla analysis in a way, is doing an atlas-based approach based on the regions. This is kind of a schematic overview that I once made. So if you have your T1 data aligned with your diffusion data, then, hold on, I'm getting a message from one of you. Thank you very much. I like making these artistic valued images, but anyway. So, yeah, so what was I going to say? Okay, so another approach to analyze data is indeed take advantage of other tools from other modalities. So with T1 weighted imaging data, these MRI data, conventional MRI data, there's many tools out there that have been, optimized for many years, trying to segment out the gray matter, the white matter, all these different regions. And obviously, if you have a tool that can segment out and parcellate the cortex into multiple regions that have, for instance, functional relevance or architectural, underlying cytoarchitectural specificity, then you could use those regions as nodes, right? And we can use those regions as nodes in a network analysis, or to keep it simple, why not just look at the diffusivity properties in those regions, so averaged within a region. That on its own is already quite valuable and can provide very useful, insightful information about disease progression or specific patterns, like looking at the inward-outward gradient of change or things like that, right? If you take that to the extreme, where every voxel is its region of interest, then we would be looking at a voxel-wise analysis, okay? I will not go into details in this workshop, but it's another approach. Think of, what I said, tract-based spatial statistics, this TBSS approach, or other voxel-wise analysis. I'm not a big fan of those. I did do a lot of research in the olden days, and I realized that image registration, even in, techniques like TBSS that try to alleviate some of these issues, I still think that the misalignment across subjects is a real problem, causing reliability issues. And so interpretation of the results is very difficult. But we can discuss about that, this technique later. But if you take like a bigger ROI, obviously, registration-wise, might not be perfect. And by that I mean using the atlas like in a free surfer analysis framework to segment out the regions of interest. But once you've done that for all the subjects and you've visually assessed like, this region, it seems to be correct for, these subjects, well, then you can do a statistical analysis. Then it makes more sense to me. All right. If you want to get even more depressed about analyzing diffusion data, here's a paper by Derek Jones and Mara Cecchiniani. 25 more pitfalls. So I suggest you have a look at them. But for most of them, you can find a way to either interpret or, correct for these issues. Okay, Khalim Mamnoon. I hope my pronunciation was not too bad, so thank you very much. Khalim Mamnoon. Yeah, that was it. Yeah. So, any questions for this last lecture? I see somebody raising their hand, so feel free to speak.
I have a question about the size of the parcellation that you would still see fit for the DTI data. Like how many regions of interest are still feasible for such a system? Like 200, 300 would it still be good, or is it too much?
Well, it's a very good question. My first reply would be like, I don't know, and this could be a cool research project where you just say like, you know what, I don't know, maybe you have some question related to maybe the two disease group versus healthy controls, and a relevant question would be like, if we choose Atlas 1, which has 100 nodes, or we choose Atlas B, which has 200 nodes, if we ask the same question, like, for instance, global efficiency of a network, well, maybe with the 200 nodes Atlas, there might not be a difference in global efficiency between the two groups, but in the other Atlas, there may well be a difference. I don't know. This is a very good question, but it warrants research. It's like, just do it. It's like almost like a Nike commercial. Just do it, right? So, it's a very genuine question. I don't have an answer, but science will give it if we run the analysis. What is correct? I don't know. So this is where the design becomes important. If you know that group 1 and group 2 are different, right? There's a pathology, and you have the assumption that network is less efficient, like this could be a consequence of the pathology, then yes, it makes sense to do an analysis, maybe with 2 atlases, and maybe this approach is very robust, and maybe you'll get the same result with both atlases, right? If you have 100 nodes or 200 nodes, maybe in both cases, your answer will be, global efficiency seems to be altered in the pathology group. It is lower than the healthy controls. Okay, then that's good news. It means that our network analysis is robust. It's not too sensitive to the choice of nodes, as long as the relevant nodes are in there. But if it is different, then it becomes interesting, because then you could think like, why would it be different? Is it because one atlas is actually a more accurate representation of different nodes that represent different functionalities in the brain? Like, are they related to other cytoarchitectonics? Is it some other property of these regions that are different from each other? This is the cool thing about scientific research, is to figure this out. But in short, I have no idea. I don't know. And this is because one aspect is that it's a fairly this research field is still in its infant years, in a way of speaking, right? It was already cool to be able to show such a network and actually compute it. But because there's so many choices that you can make, because of all the degrees of freedom, I can imagine that there will be big differences depending on choices that you make. So yeah, plenty of research left for you to tackle. So sometimes I feel like it's up to the new generation to figure this out. But yeah.
Sorry, I have also a following question. Yeah. So about the atlases that are volumetric or surface space, which one do you think makes more sense for using with the DTI?
Can you repeat that? Because I couldn't hear the first part.
Okay, the surface space atlases or the volumetric atlases. So if I want to combine one with the DTI, which one would you say makes more sense?
Well, Both, because a surface-based one, then you're basically referring at the interface between white matter and gray matter, right? And the volumetric atlases, well, the way I see it, they have regions of interest in the entire brain, and you could probably also compute the surface-based equivalent to it by just saying like, this is gray matter, this is white matter, this is at the interface. And so conceptually, I don't see a difference because, well, if you're not including the white matter as a node, so I wouldn't include, let's say, a white matter region as a node, I would then focus on the volumetric atlases, only the gray matter regions. And then, in my view, it would mount up to the same results. So if that surface-based atlas showed similar regions compared to the, volumetric-based ones, then, the only difference is the implementation of the actual framework. So in Explore DTI, the way it's implemented in Explore DTI is that everything is volumetric-based. So when you're doing tractography, if a point at some point literally falls in an ROI, then it states it's connected to that region of interest.
Thank you.
All right. Any other questions? Okay.
If no one else is asking, I would also have a question about like this method that you said you showed, CSD. What was the short form of it?
Yeah, CSD.
Yeah. How like time wise, how different it is with the other method?
Okay, so from a computational point of view,
yes,
it takes a bit longer to compute. Depending on the settings that you choose, you're looking at maybe twice as long to maybe up to 5 times as long in terms of computation. Well, I'm now, I've recently done a CSD calculation. I think it took 15 minutes on a 6-year-old laptop. So, not too bad. You could probably improve the speed by, either re-implementing it on a graphics card or something like that. For most applications, especially in research, I don't see the need to, improve the performance per se, but it depends on your application. So obviously, if you're working in a dedicated neuroimaging center with pre-surgical applications, you may want to do this like almost real time. But then you've got dedicated companies that implement this, fully optimized and everything. I don't care about it too much. So from an Explore DTI point of view, if you can compute something, like I said, either things are quick, like within seconds, or you can take a few minutes and then you can have a cup of coffee, or you can run things overnight. And what we'll see, or what I will show with the pre-processing, for instance, that can take maybe even an hour or something like that, depending on data size and things. But if you do something like that, you would probably do it on maybe 10 subjects or even more, and then you can run it overnight or over the weekend, right? So it's all about being clever when to process, how to process, and why to process stuff. So.
Thank you.
All right. By the way, I'll give you some good news and bad news. The good news, well, let me start with the bad news. Okay. The bad news is, I just glanced over, it's 2:45 my time. So I guess Teherani time is like 2.5 hours further down the road. So I guess you guys are almost getting hungry for dinner. Maybe not, but So the bad news is, at 4, I have to leave. The good news is, I'm willing to schedule another meeting, maybe in a few weeks, to continue with where we're gonna stop today, right? So that's something I'm happy to do. So because I realize we're kind of running over time, doing the hands-on. We should do this after the break, but it's almost 2:45. And I think it's more important that I explain things properly and that you have ample time to ask questions than to just rush it and then you feel like, we've covered everything, but everything in a bad way. So it's better to do less in a better way, and then the next time do it another time. Well, it's nice to see the kind of agreeable reactions there, because then it will have the additional benefit of all of you who are struggling to install the software. Then you have plenty of time, think of weeks, to actually run the software, and hopefully you guys can help each other out as well. Like if somebody was able to do it, and maybe those that didn't, obviously you can ask me or go to the forum. There's a forum where you can ask questions and see whether to, how to fix this. So having said that, I'm giving you the option as follows. I know it's sunny in Tehran. See where this is going, right? Either we continue now for roughly an hour, because I do need a little break now for some coffee. We continue for another hour, or we kind of wrap it up with more questions now, like just some chit-chatting. I'm happy to discuss other things as well, maybe career paths, things like that. I know you young people, there's uncertain situations, not just geopolitically. I know that's also an issue. I know I've been to Iran many times now, but also from, kind of, career-wise, what is interesting. And then we can chit-chat about that a bit further in a few minutes after a little break. And then continue with the hands-on on another day. And then we have a dedicated day for hands-on. I see Masha raise her hand many times, so I'll give her. What do you think? Just comments. Okay. Well, I'm happy that you agree. I must admit, I am also getting a bit tired. I've been up since 7. I've been talking, and my voice is getting a bit weird, but that's fine. So, so yeah, if you want, we can now have a few more questions and some discussion. And obviously, for those who want to leave, I guess you can leave. You're allowed to leave. That's fine. And in the meanwhile, I see more hands being raised, so I'll ask Masa to be the moderator here. So maybe you can say who can ask questions and whatever.